Shift registers, like counters, are a form of sequential logic. Sequential logic, unlike combinational logic, is not only affected by the present inputs, but also by the prior history. In other words, sequential logic remembers past events. Shift registers produce a discrete delay of a digital signal or waveform. A waveform synchronized to a clock. A repeating square wave is delayed by n discrete clock times, where n is the number of the shift register's stages. Thus, a four-stage shift register delays data in by 4 clocks to data out. The stages in the shift registers are delay stages. Typically, type D flip-flops or type JK flip-flops. Basic shift registers are classified by structures according to the following steps. First is the serial in, serial out type shift registers. Second is the parallel in, serial out. Third is the serial in, parallel out. Fourth is the universal parallel in, parallel out, and the ring counters.
Serial in or serial out shift register means delay data by 1 clock at a time for each stage. They will store a bit of data for each register. A serial in serial out shift register may be 1 to 64 bits in length, longer if register or package are cascaded.
If we see the output of this first stage, then it will become 0. And likewise, for the remaining 3 stages also, the output will become 0. And now, whatever data which was earlier stored in this last flip-flop will get discarded. So these outputs will be available at the output line just after the propagation delay of the flip-flop. And since the output of the one flip-flop is connected to the next stage, so these outputs will act as an input for the next stage during the next clock age. So now the next bit which we want to transfer is equal to 1. So the same 1 should be applied to the input. And at the same time, if we see the present inputs for the remaining 3 flip-flops, then they are 0, 0 and 0. So now at the next clock age, these 4 flip-flops will respond to their present inputs. That means now the output of this first flip-flop will become 1. And similarly, these D2, D1 and D0 will respond to their present inputs. And once again, now whatever data which was earlier stored in this D0 will get discarded. That means after the second clock age, this will be the output of the shift register. And these outputs will act as an input for the next stage during the next clock age. So now at the next clock age, the data which we want to move into the register is equal to 0. So the same 0 should be also applied to the input just before the clock age. And at the same time, if we see the remaining 3 inputs to the flip-flop, then they are 1, 0 and 0. So now at the clock age, all the 4 flip-flops will respond to their present inputs. That means now the output of this D3 will become 0. And similarly, the output of this D2, D1 and D0 will become 1, 0 and 0. And earlier, whatever data which was stored in this D0 will get discarded. That means after the third clock age, this will be the data inside the shift register. And finally, the data which we want to shift into the register is equal to 1. So the same 1 should also apply to the input just before the next clock age. And at the same time, if we see the inputs for the remaining 3 flip-flops, then they are 0, 1 and 0. That is the output of the previous stage. So now at the clock age, once again, all the 4 flip-flops will respond to their present inputs. That means now, just after the clock age, the output of this first flip-flop or the output of this D3 will become 1. And likewise, the output of this D3, D2 and D0 will become 0, 1 and 0. And whatever data which was earlier stored in this D0 will get discarded. So in this way, after the 4 clock pulses, this 1010 data will get shifted into the register. And as you can see, at every clock age, the data is moving from left to right side. And that is why this register is known as the shift right type of seesaw register. So if you see the same thing in the timing diagram, then this is how it will look like. So as you can see, at the clock age, the input to the flip-flop is equal to 0. and this input is applied to the MSB. That means at the first clock edge, the output of this Q3 will remain 0. Similarly, at the next clock edge, the input to the D3 is equal to 1. Therefore, its output will become 1. But as you know, the flip-flop will take certain time to respond to the present input. That means the output Q3 will change only after the propagation delay of the flip-flop. Likewise, the next input to the flip-flop is equal to 0. That means at the third clock edge, the Q3 output will become 0. And once again, it will take certain time to respond to this present input. Likewise, at the fourth clock edge, the input to the D3 flip-flop is equal to 1. And therefore, its output will become 1. So this is the timing diagram of the Q3 output. And since the Q3 output is connected to this D2 flip-flop, so this D2 flip-flop will respond to this Q3 output at the every clock edge. So here at the clock edge, since the Q3 is 0, so the Q2 will also remain 0. Similarly, at the second clock edge, since the Q3 is once again 0, so this Q2 will remain 0. Likewise, at the third clock edge, since the Q3 is equal to 1, so this Q2 will also become 1. But as you know, it will take certain time to respond to this Q3 output. Likewise, at the fourth clock edge, since the Q3 is equal to 0, so this Q2 will become 0. And once again, it will take certain time to respond to this Q3 output. The timing diagram of the Q2 output. Similarly, we can also see the timing diagram of this Q1 and Q0. So as you know, this Q2 output is connected to the D1 input. That means this D1 flip-flop will respond to the Q2 output. So once again at the first clock edge, since the Q2 is equal to 0, so this Q1 will remain 0. Likewise, at the second and the third clock edge also, this Q2 output is equal to 0. And therefore, this Q1 output will remain 0. And at the fourth clock edge, if you see, now this Q2 output is equal to 1. Therefore, this Q1 output will also become 1. And once again, it will become 1 only after the propagation delay of the flip-flop. So this is the timing diagram of the Q1 output. And likewise, we can also see this Q0 waveform. So as you can see, at every clock edge, since the Q1 output is equal to 0, so this Q0 will remain 0 up to the 4 clock edges. So just after the first clock edge, if you see the outputs of this Q3, Q2, Q1 and Q0, then they are 0, 0, 0, 0. Similarly, after the second clock edge, if you see these 4 outputs, then they are 1, 0, 0, 0. That is the third row. And likewise, during the third clock edge, these outputs are 0, 1, 0, 0. That is the fourth row. And lastly, after the fourth clock edge, these 4 outputs are 1, 0, 1, 0, which represents the last row. So in this way, with the help of the timing diagram also, we can also see the working of this shift right register. So of course, if you want to take this data outside, then once again, we will require 4 clock pulses. And as you can see, first of all, this LSB will move outside. So in this serial in serial out type of shift register, once we move the data inside the shift register, then we need to make sure that this input line will get disabled. Because if this input line is not disabled, then the random data will be available at the input side.
Parallel in, serial out shift register do everything that the previous serial in, serial out shift register do plus input data to all the stages simultaneously. The parallel in, serial out shift register stores data, shift it on a clock by clock basis, and delays it by the number of stages times the clock period. In addition, parallel in, serial out really means that we can load data in parallel into the stages before any shifting ever begins. This is the way to convert data from the parallel format to the serial format.
Load is high in this particular case. And this happens to be a 1, 0, 1, 0 here. what's the output of those AND gates? 1, 0, 1, 0. But if load is 0, I mean, don't load it right now. Remember, anything ANDed with 0 is a 0. You're not loading anything. Okay? But just to make matters slightly more confusing, we want an active low load. So let's invert that signal right there. Okay, so now when load is a 0, it's a 1 there. And 1, 0, 1, 0 gets loaded in. Okay? Not too difficult there. But now we've got to go ahead and combine that whole functionality of parallel in with our previous discussion of serial out. So we've got to come up with a situation where we can either have parallel in or serial out. And the key word I put there is obviously an or. So what we've got to do is definitely put an OR gate. But we've already come up with we've already did the logic diagram for our parallel in, but now we've just got to OR it with our serial out. And that is a shift command. And shift, just to be thrifty, is actually the opposite of load. So we only really need one of those. So it's not like there's a separate shift command and a separate load command. If we want it to shift, i.e. to read, take data out, we give it a 1. If we want to put data in, we give it a 0. And we'll go ahead and show you how that works by putting our shift, i.e. enabling our serial data out with this combination of parallel in. So what I've done here in this diagram is I've redrawn our load with our ands there, and now I've done portion of the shift and I've done that in red. Our parallel data, I've done that in green. Okay, so let's describe this here in further detail, and we'll expand upon the shift, i.e. the serial out. Okay, so like I said, we've only got one command, shift and active low load. So what's the red? That's shift. Okay, in shift, we want to pass the previous stage's Q to the next stage's D. And we do that with these ands, ors. Okay, so think from the perspective of shift. So when shift is 1, this AND gate, what's it going to do? Well, it's going to pass the previous stage's Q to the next stage's D. And basically it's going to go like this, in through here, through there. Basically, we've made a serial out. We're passing the previous stage's Q to the next stage's D. So let's go ahead and continue this here. Okay, so what I've done here is basically I've done all of the serial out stuff in red and all of the parallel in blue. So let's visit again step by step here. So we're given this load line a 0, which makes this a 1, which, what was our number before? I can't even remember what it was. I'm just going to say 0, 1, 0, 1, 0, 1. All right, so when that load line is 1, what's going to get passed to here? A 0, a 1 here, a 0 there, and a 1 there. But now think about what's happening when load is 0 what is shift? That's also a 0. So these AND gates here, that's getting a 0. That's getting a 0. That's getting a 0. Placing a 0 there, and a 0 there, and a 0 there. So from the perspective of this OR, 1 OR 0, a 1. 0 0, a 0. 1 OR 0, a 1. We've already done this analysis, that's a 0. So what have we done? We've loaded 0, 1, 1, 0, 0, 1, 1. Ta-da! Clock pulse comes along, bang. That is what our Q inputs are. Excuse me, our Q outputs are. 0, 1, 0, 1. Now, we want to go ahead and shift. And how many, in this particular case, how many clock pulses is it going to take to get the data off? Well, there's 4 bits, so it's going to take 4 clock pulses to get the data off. Let's go ahead and clean this diagram up, and we'll go ahead and see how that's done. Okay, so I went ahead and cleaned up the diagram here, and now we're going to show you, well, previously what happened here is we parallel end 0, 1, 0, 1, and that I just showed you how we got 0, 1, 0, 1 on the outputs of the individual stage, respectively 0, 1, 2, and 3 of our flip-flops. So that was fine for load, and now we want to shift. So using our ingenious single command, load, shift, that changes to 1. So what's happening on this blue bus here? That's a 0 all the way across. So this AND gate here is a 0. That's a 0. That's a 0. That's a 0. So regardless of what's going on there, those AND gates are always going to produce a 0. But now it's our shift. Our shift command is basically enabled a path from the previous stage output to the next stage's input. Okay? Because there's a 1 here. And in this particular case, we've got a 0 there. And it's a 0. So 0 or 0 is a 0. We basically passed this 0 on to the next stage, 0. Same thing here. We've got a 1 and a 1. That's a 1, 1 or 0. So 1. We've passed that 1 on to the next stage. And now 0 and 1 is a 0. 0 or 0 is a 0. We've passed that previous stage's output onto the input. Next clock pulse comes along. The previous stage's input is loaded into the next stage. And basically what's happening, we were at 0, 1, 0, 1, 0, 1. Next clock pulse comes along. We've shifted it, passed it on, passed this guy on, passed this guy on. And there's somebody over here that's reading on the output. So just read a 1. Then it's going to, I don't know what happened there. Pass that 0 to there, pass that 1 onto there, pass that 0 onto there, and finally that 0 is kicked out at the very end. Ultimately, how fast did it take to load? Well, it's parallel in 1 clock pulse. How fast did it take to read? Well, it's 4 bits coming out in a serial fashion, 4 clock pulses. Okay, super fast load, slower download. Okay. Let's talk about one device in particular, the 74165. That's an 8-bit parallel input serial output shift register. And additionally, it can also act as a serial in, serial out shift register. Okay? So that's a parallel in and a serial in. Serial out shift register. And that's 8 bits. And ultimately, what that guy looks like That's your ins. It's a serial out. So there's only one out. It's got that shift, active low load. It's got our clock. It's got this special thing called a clock inhibit. So if you basically want it to ignore the clock, just put a high on that clock inhibit for the brief moment you want to go ahead and ignore it. That means, okay, shift, shift, okay, stop. Everybody stay where they are. Okay, shift, shift, shift. Basically, that's what a clock inhibit is doing. And then finally, what's dangling off here? SER, like I said before, you can also use it as a serial in too. So 74165 is both a parallel in and a serial in, but it's only a serial out. 8-bit shift register. Shift register, 8 bits. Okay, let's talk about our last combo is the parallel in, parallel out shift register.
Serial in, parallel out shift register. A serial in and parallel out shift register is similar to the serial in and serial out shift register, in that it shifts data into internal storage element and shifts data out of the serial out, data out, and pin. It is different in that it makes all the internal stages available as outputs. Therefore, a serial in, parallel out shift register converts data from serial format to a parallel format.
Okay, so again, we want to feed in a value 1011 into our serial in, parallel out shift register. And again, it's going head first. It's MSB to LSB. So MSB 1011, head first into that. And that is the data diagram pictured here. Again, let's assume everybody's initially reset. So at clock pulse 1, this guy, Q0 was a 0. Q1 is its data input is the previous stage's output. Now, okay, clock pulse 1 comes along. Q0 is reading data input right there. So let's account for a little bit of a delay. And it's going like that. Okay, so Q1, it's reading Q0 there. So it stays at 0. Same here. Same here. Second clock pulse. Q0 reading D in. It's reading a 0. Counting for the delay. Goes like that. Q1, it's reading Q0 right there. Counting for the delay. Goes up to 1. Again, see how that block is just shifted over there, hence the name shift register. 0, 0. And now we are reading here. 1. Reading there. Count for the delay. Reading there. Notice the shift. 0 there. Okay, now we're going to read here. Stays a 1. This one goes up to a 1. This one's reading a 0. This one's reading a 1. Shifting. Okay, next clock pulse. What's going on here? Are we already full here? Yep, we are. We already got all 4 bits in there. And again, we're reading 1, 0, 1, 1. And how many bits does it take to, because I mean, we're already at 1, 0, 1, 1. How many clock pulses does it take to read it? Just 1. Because basically, they're all simultaneously boom, 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 going out. 1, 0, 1, 1. Again, head first. MSB to LSB. Okay, you want to go ahead and clear this guy. It's going to take, again, those 4 other pulses. 1, 2, 3, 4 to successively shift those zeros into our positions there for the Q3 through 0 bits. Okay, so again, advantage of a serial in, parallel out. You stick in serial in, but you can fast read them out. So it just only takes 1 clock pulse to get them out. If we kept going here, we could actually use this as a serial out also. You know, kept on feeding those clock pulses in and progressively cleared things out that way too. But typically a chip that you buy off the shelf at NETTL is normally strictly a parallel out or parallel in. But if you're tricky, you could use it either way. So matter of fact, let's talk about one of those, specifically the 74164. That is a serial in parallel out shift register. It's an 8-bit. So what is its logic symbol? So it's obviously got a clock, it's positive edge, SRG, shift register 8, and it's got Q0 through Q7 outputs. How many inputs does it have? Well, serial in, there's 1 door in ordinarily, but no, this thing's special. Actually has 2 doors in. And A and B are actually hooked up with a NAND. Okay, so this, if you could actually just imagine that same shift register that I just drew upstairs with just a NAND with A and B. So you've got a little bit of logic connections there. Where this is actually it's implemented with SR latches. But just think of it as A and B combined as a NAND, and that logical combination, that's your single door into the bus. There's also a clear, which I believe is asynchronous. Let me go check a data sheet. Asynchronous clear. Active low. Asynchronous clear. Okay, that is about it for serial in and parallel out shift registers. And we're going to move on to parallel in, the opposite, shift serial out shift registers.
Parallel and parallel out. Universal shift register. The purpose of parallel and parallel out shift register is to take and parallel data shift it. Then output is as shown below. A universal shift register is a do everything device in addition to the parallel and parallel out function.
And as it gets to their destination, everybody gets off. The other side, parallel out. Nothing too special about a parallel in, parallel out shift register. What is special is this guy right here, the 74195. This is a 4-bit parallel access shift register, but it's not just limited to parallel in, parallel out action. It is pretty universal in nature in the fact that it has a serial in on it, just like we discussed with the 74165. And if you just give it enough shifts, in this case 4, you could just use Q3 output as the serial output. Therefore, it's serial in as well as parallel in, and it's serial out as well as parallel out, depending on what mode you use it in. And so how this guy looks is it's 4 bits. So here's our loads, our data ins, and here's our outs. And what you do is when you give them a load, you put a 0 right there. These guys go in, they're immediately available as a parallel out. So that's parallel in, parallel out operation. Obviously, there's a clock. So basically, it's giving a low, active low load. The next clock pulse comes along, I should say. Let's say that's 0, 1, 0, 1. Next clock pulse comes along, 0, 1, 0, 1. Okay, so that's in its plain old vanilla parallel in, parallel out mode. There are other couple things that we should discuss about this guy. Well, it's got a clear. That's an asynchronous clear. So give a 0 on that guy, it clears everything out. So we go ahead and do a 0, regardless of what's happening with the clock, or what's on the data. That's on the output there, because active low clear doesn't matter what the clock's doing. There is the serial input, and this is actually 2 inputs. There's a J and a not K. Okay, we have been analyzing these shift registers as if they were D flip-flops. Well, in this case right here, this J not K input is the input to the first stage flip-flop Q0. So if you want to set it, a normal JK flip-flop, you got to give this a 1, and a K, you got to keep it a 0. But since that's not K, you got to give it a 1. So that's the serial input for stage 1. And that can be, depending on how you put this here, you can set it or reset it. You have to, that's basically your 1 door there. Okay, and like I said earlier, if you go ahead and give this guy enough, oh, I forgot to tell you about this, the multifunctionality of the load. So if you want to use it as a serial out, there's this thing here. There's an active low, which is a 0. But if you give that a 1, that's shift. So shift load is the same pin. So load, if it's a 0, it loads these guys. If it's a 1, it shifts the data to the right. Okay, so we load, we go ahead and let's say we load 0, 1, 0, 1. 0, 1, 0, 1. Then we make shift 1. And next clock pulse comes along, everybody shifts right 1. Next clock pulse comes along, everybody shifts right 1. Next clock pulse comes along, and we've cleared that registered. Well, not really, because that's 0. If it was a 1, just to make sure, give it 1 more clock pulse to clear it out. And while we're at it, let's just do a timing diagram of this guy right here, because it is such a cool device and very universal. Okay, here we go. Here's the inputs for our 74195 4-bit parallel access shift register, which, as we know, is a more of a universal type device. And forgot to put the J and not K inputs there. 1 second. Here we go. Okay, so we are starting off. What are we starting off with here? First off, we got these guys hanging out here on the data inputs. D3, D2, D1, D0 has 1, 1, 0, 1 on it. Okay, and we are starting off with active low clear right here. So what are our outputs? Q0, Q1, Q2, Q3. It is clear because it's been cleared. Okay, notice what's going on here. Shift load. It's high all the time. So all it's going to do when it's high, it says it's going to basically shift the data. Okay, so next clock pulse, and it's positive edge triggered. Our first clock pulse has come along. There's no J inputs, there's no K inputs, so it's going to shift the 0 to the next one. So Q0 goes to Q1, Q1 goes to Q2, Q2 goes to Q3, and Q0, another fresh 0 is loaded into it. But now, next clock pulse comes along. There is a J input, there is a K input. And like I said before, excuse me, not K input. So that is the input to the first register. So this guy goes there. Okay. And we're still in this shift command. So Q00 was shifted to there, Q10 is shifted to there, Q30 is shifted to there. Next clock pulse comes along, this guy right there, Q0's 1 is shifted to Q1, and so on and so forth. Next clock pulse comes along, which is this guy, and by the way, there was no J and K input on that one. It's shifted again. Making sure I'm accurate here. Okay, but this next clock pulse comes along. Ordinarily, we would be shifting, but check this out. We got an active low load. What is being loaded onto our Q outputs? These D inputs. So we got our 1, our 1, our 0, our 1. So I should actually delete that line right there because there's no transition. Okay, so then that active low goes away and we're right back to shift land. And now this is just going to behave just like a serial out shift register, which we've already done the analysis. Okay, so I'm going to draw the clock pulses right there. So by the way, I've abandoned that whole delay thing right now because you should understand what's going on here. It's basically the shifting. You don't really need to know what it is, what it was at that present time. Just understand that it was reading it, and now it's shifting at next clock pulse. So this 1 goes there, that 0 goes there, this 1 goes there. Next clock pulse, 1. We're putting zeros on there. And finally, we got 1, 0, 0, 0. And then finally, last clock pulse there, we've cleared our shift register. How many did it take? It took 1, 2, 3, 4 clock pulses to clear our 4-bit shift register. Okay, so parallel in, parallel out shift registers, and we used a universal device, the 74195, with a bunch of different inputs, notably our shift and load and our combined serial inputs. And the fact that we were using an active low load, we basically loaded our 1101, what was on our D inputs at that time, and otherwise it was behaving just like a serial out shift register. Okay, so we'll go on to bidirectional shift registers.
Ring counters. If the output of a shift register is fed back to the input, a ring counter results. The data pattern contained within the shift register will recirculate as long as clock pulses are applied. For example, the data pattern will repeat every 4 clock pulses in the figure below. However, we must load a data pattern. All zeros or all ones doesn't count. Is a continuous logic level from such a condition useful?
In this class, we are going to discuss about ring counter or shift register counter. This is also one of the type of synchronous counters. So, in which we are having similar clock pulse for each and every flip flop. You can observe similar clock pulse for each and every flip flop here. And now, so this ring counter is similar to shift register counter, shift register. Why? Because here you can observe here without this feedback connection. So, it will works like shift register. We are just ringing this connection. So, we are just connecting output to input as a ring. That is why this is called as ring counter or shift register counter. So, without this, this is going to work as shift register. So, the special case of this ring counter is it is going to count n number of states only. In the previous, when I am introducing counters or when I dealt with asynchronous or synchronous counters, I told you that we are having 2 power n states for a counter. That means a counter can count n numbers or n states, n bits. A counter may have n bits and it may have 2 power n states. That I told you in the last classes. That is the basic one. But here this ring counter will count, so will have only n states. So see here, for example, if you are having 4-bit ring counter, then it may have only 4 states. So I am considering the initial data of this register is 0001. So that means, so like this I am considering. So 0001 means, so here I am considering 0 and here I am considering, so where I am considering 1 means at the place of Q1 I am considering 1. These are the initial contents of your data. 0001 at Q1 you are having 1. This is your initial contents of your counter. Then you need to count. So, how many states it is required to get the same state? That means to get same 100 like this, how many states it needs to pass, that you need to check. So, now I am checking here. So, before going into the process, I want to tell you something about D flip flop. What is the working of D flip flop means? It is just data transmission. Whatever data we are giving for D flip flop, when positive edge of clock came, that D is given to output. That is it. D flip flop is not doing any toggle operation or anything, just giving whatever input is there, it is giving that input to output when clock is there. So, now and here as we are having synchronous clock, we need to get ready with the inputs every time. So, to give first clock pulse, first I need to get ready with the inputs. So, I am just noting inputs for each and every flip flop. This 0 will come here as input at the time of first clock pulse. So, this 1 is given here, this 0 is given here, this 0 is given here whenever we are giving first clock pulse. So, now I given first clock pulse. What that D flip flop is going to do means just giving that input to output. That means this 0 will come here, whatever 1 is there, that 1 will come here and this 0 will come here, this 0 again will come here. So, that means after giving first clock pulse, your Q4 is equivalent to 0 and your Q3 equivalent to 0 and your Q2 is equivalent to 1 and your Q1 is 0. Now, to give your second clock pulse, again you need to get ready with the inputs. That means whatever 0 is there, you need to take that 0 here. Okay, taken, and 0 is available here, 1 is available here, 0 is available here for second clock pulse. So, now yes, I given second clock pulse. What D flip flop is doing means whatever input available, that is throwing to output. So, now if I given second clock pulse, so at the time of second clock pulse, these inputs are ready for this particular flip flops. So, this 0 will come here, this 0 will come here and whatever 1 is there, so that will come here and whatever 0 is there, that will come here. So now, so after second clock pulse application, the outputs are Q4 0, Q3 is equivalent to 1, Q2 is equivalent to 0 and Q1 is equivalent to 0. Now, to apply third clock pulse, again you need to get ready with inputs. That means, so this flip flop is ready with 0 and this is ready with 0 and this is ready with 0 and this is ready with 1. Now you can apply your third clock pulse. When I applied third clock pulse, that means third rising edge came. So then this D flip flop taking this 0 to here, this 0 to here, this 0 to here, and whatever 1 here is there, that's going to here. You are getting 1 here. So now, so here after application of third rising edge, your output is 1 0 0 0. So after application of third clock pulse, you are getting like this. To apply fourth clock pulse, so to apply fourth clock pulse, again you need to get ready with your inputs. This one will come here before application of fourth clock pulse, and this 0 is ready for this 0 is ready for this 0 is ready for this. So here when I applied fourth clock pulse, this 1 will come here and this 0 will come here, 0 will come here and 0 will come here. So now, so after application of fourth clock pulse, my outputs are Q4 0, Q3 0 and Q2 0 and Q1 is equal to 1. Here you can observe the same value equivalent to initial state. So counter will stops counting. So that means it's passed through 4 states to count the 4-bit data. It passed through 4 states to count the 4-bit data. That means for a ring counter you require n states, 4 states, n clock pulses. You require n clock pulses. You can say nt seconds will take. So t is dependent upon your time cycle duration. So it will take n states. So each state is having some t duration. So it will take nt seconds for a ring counter. So in exams they will ask how much time it will take for ring counter, how much time it will take for asynchronous counter. So how much time it will take for some synchronous, normal synchronous counter, how much time it will take for Johnson's counter or twisted ring counter. They will ask like this. So that's dependent upon this. So now it stopped means initial data. If you got initial data means you need to stop that counting and you need to count the number of states. This is the process of ring counter. Here in this process also you can see this one is moving with ring like structure. This one is just shifting and we are counting the number of pulses. How many shifts it's required to get the same data finally. So we are counting that value. So this is about ring counter or shift register counter.
Your presenters: Jevi Hans Book, John Lester Kajandig, Cedric John Panazales, Dave La Rosa, Myra Reyes,